Thank you very much for introduction, and as always, it's my great pleasure to give a talk here, especially perhaps the largest audience ever for Discrete Math seminar. So my talk is about the external number of subdivisions. So apparently I forgot to add this preposition in the notice, so this is joint work with David Conlon, who was my supervisor when I was in Oxford, and David repeatedly told me that I'm bad at prepositions, and I forgot to add on this time. So let me start with a definition of extremal number. So extremal number of graph H is the maximum number of edges in all n vertex H free graph. So this is a definition. So we take the maximum number of edges possible over all H-free n-vertex graphs. So let me give a few examples. So there's a famous and classical theorem by Turan in 1940, I think, that actually determines the external number of the complete graph KT. So in this case, it gives 1 minus 1 over t minus 1. So let me cheat a little bit. Because so the upper bound is kind of clear, and that's what actually Turan proved. And the lower bound construction is just given by the t minus 1 partite, complete t minus 1 partite graph. So so up to the divisibility of n, there's a small terms in the lower bound construction, but let me just ignore that. Extending this result, probably some people say that Turan theorem is a fundamental theorem of external graph theory, like fundamental theorem of algebra or fundamental theorem of calculus. So extending these results, Erdős, Stone, and later slightly improved by Szymonowic. They determine the asymptotic behavior of external number of any h, which is as follows. So here chi of h is the chromatic number of h, and so the external number of h is asymptotically the number of edges in the complete chi h minus 1 partite graph. I mean the edges in the complete chi of h minus 1 partite graph. So this seems quite satisfactory at first glance, but apparently when my graph is bipartite, which means the chromatic number is just 2, this doesn't tell much about the external number. So if I put chromatic number to be 2, then what I'm getting is just the literal of n squared. And hence, it's a natural question to ask if there's an improvement of this Erdős-Stone-Szymonowic theorem for bipartite graphs. The question, there exists a better bound? for particularly bipartite H. And this question really is a major open problem. Lots of major open problems in extremal graph theory are phrased in this form. And people really tried hard to nail down this type of questions, and only few of them succeeded. So firstly, perhaps the most successful example is about the 4 cycle. So for 4 cycle, there are multiple literatures, but firstly, Kuvari, Shosh, and Turan, and later by Freddy. Now we know that the asymptotic behavior of the extremal number of 4 cycle up to the constant. So, and as far as I know, this is the only example we are succeeded in knowing the right constant. So apart from this result, we only know the asymptotic behavior except the constant itself in front of the n to the something. So later, there's a result by Bondy and Shimonovitz. Who proved the extremal number of even cycle is at most 1 plus 1 over k. So apart from the constant itself, it improves the result, the estimate for the 4 cycle. And this is tight, known to be tight, say, known to be tight, only for k, well, k equals 2 and 3 and 5. We still don't know this is correct for 8 cycles, say. So it's a bit frustrating, but there are some other results. So another example is the result by Kuvari.
So is there a case where it's known to be not tight? Or?
No.
Okay.
No. So it's conjecture that this is tight for all even cycles. However, well, some people say it might not be for 8 cycle because, yeah. But the lower bound construction is the harder part. We really have to construct some graph with that much edges with even cycle free. So often it relies on some algebraic construction. So for example, this 4 cycle free graph comes from the projective plane, the incidence of projective, the lines in the projective plane. And yeah, we really don't know good constructions. We only know few good constructions for lower bounds. So another result by Kuvari, Shosh, and Turan. This is again very classical result, saying that for complete bipartite graph, which is another fairly natural example to consider, we have 2 minus 1 over s when s is at most t. So this is another estimate. And this is known to be tight. Let me just omit the known to be. Tight for when t is fairly larger than s, like in the order of s factorial. And the construction is again kind of algebraic construction. And another successful estimate is by Fodry and Shimonovitz. So it extends this result by Bondy and Shimonovitz, saying that the theta LK, say. So the theta graph LK means that I have the k edge. So this is length k path, and there are L of them between two vertices. So it's, in some sense, it's a generalization of the even cycle. So even cycle is just k path, just two k path with same end and starting vertex. So for this guy, we know that the same kind of bound holds. So this really generalizes the result by Bond-Shimonovitz. And it's again known to be tight for when L is large. Large for fixed k, which means if we have sufficiently many copies of path between two vertices, then we know that there's a right construction. And this is by David, which is built on the work of Boris Book, who kind of reproved with a slightly worse bound for this Kovarev-Turan result. Yeah. And yeah, so far there are some results. And like, there are only very few general results. Like something like if my bipartite H satisfies this condition, then the external number satisfies that. And one of those few examples is by Freddy in 1991, answering a question by Erdős, and later reproved by Alon, Krivelevich, and Sudakov in 2006, I think. Yeah, says the following. So if my H has max degree R on one side, which means given a bipartition, I have a max degree R on this side or that side. Yeah. Then the external number of H is big O of n minus n to the 2 minus 1 of R. And this is more or less tight. So for example, for R equals 2, this is tight because if R is 2, then you have this. And well, apparently this full cycle has max degree 2 on one side. Actually, yeah, obviously. So this is tight. And for general R, because we know this KST-free construction for t larger than s. So this is again tight for for general R, because we have KRS, say this is theta of R if S is sufficiently larger than R. So in some sense, this result cannot be improved. But I'm going to talk about the improvement on this result today. So the natural statement would be as follows. So we actually improved this result here.
H가 bipartite고 R이 extremal number가 n3고 2인 게 타이트하다고 했잖아요. 근데 저기서 n3k도 h bipartite이면서 maximum number가 2니까 똑같은 조건 만족하는 것 같은데 타이트하다니까 어떤 의미로 타이트하다는 건지
K to 3요.
그 C to K.
C to K.
bipartite이면서 maximum degree
근데 이게 so his question was how this bound relates with this bound. And yeah, the answer is actually this is better than this if k is larger than 2. And hence, it's not a contradiction. But, I mean, for max degree R on one side, if I carry on this condition, max degree 2 on one side, we can't really expect a better bound because of the full cycle. Because if I just carry on this condition, and there's no kind of general bound that beats this one. So that's what I meant. Yeah, so my result with David states that if my H has max degree R, max degree 2 on one side, and if it's full cycle free, which exactly excludes the example that really attains this bound, then we can do better. For small some constant, we actually give a better exponent estimate. So that's a statement. And yeah, we conjecture that the same would hold for general R, but let me just postpone this discussion later. And yeah, so this is our result. And apparently, after we submitted this paper, we found an old literature written by Erdős that really asked this question.
Oh.
Yeah, so it's the other way around. Yeah. So what Erdős told was so what he told is there's an unpublished result. So it was unpublished in 1988, but I think it's still unpublished. There's an unpublished result by Fodor and Shimonovitz proving that the extremal number of one subdivision of K4. Let me explain what the subdivision is later, but let me just give the picture first. Yeah, so this is a one subdivision of K4, or I'm just going to say the subdivision of K4. It's little of n to the 3 halves. And Erdős asked that for one subdivision of any kt, if the same bound holds. So he exactly said just perhaps this is smaller than that. And we answer the question. Yeah.
Any cash price?
No. So, well, this really is a question than a conjecture, because what he said is perhaps this. Yeah, that was it. Yeah. So as I sketched it here, another way to look at this problem is to look at the subdivision. So the subdivision of a graph H is given a graph H. I'm just going to replace each edge by a k edge, k minus 1 edge path. So given H, something, say, for example, full cycle. Then if I replace, T. Okay, let me just say HT, replace each edge by T plus 1 edge path. replace edge of h by t plus 1. So for example, as I drew here, the one subdivision of a triangle is a 6 cycle, and the one subdivision of K4 is the one subdivision of K4, and I'm going to denote by HT the one, let me just say this subdivision of KT. Yeah, so, sorry, yeah, this should be HT. So a moment's thought would just give you that any max degree 2 graph on one side that is C4 free is a subgraph of HT. You all agree with that? Yeah, because there's no multi-edge. I mean, if there's a multi-edge, then it will give you a full cycle, if and only if statement. Yeah. So another way to look at this theorem is, so restated, the external number of HT is at most n to the 3/2 minus some small constant. So before getting into the proof, let me give a SketchUp proof of the result by Freddy following the technique of Alon, Krivelevich, and Sudakov. So yeah, to beat this bound, we have to understand what they do. Well, it's not always necessary, but we started from understanding the proof, and with some extra idea, we managed to improve the bound. So the proof by Alon, Krivelevich, and Sudakov is by the dependent random choice lemma, which is another a very general, powerful tool in extremal combinatorics. So let me give a proof of Freddy's theorem by Alon, Krivelevich, and Sudakov. Perhaps just SketchUp proof. So for r equals 2 to avoid some extra complication. So here's a proof. So given a bipartition A, B, so my graph G is a bipartite graph on A union B, and we may assume that A and B are of the same size, approximately the same size. And yeah, we may assume that G is bipartite. There are some technical conditions, technical tools to prove this statement, but let's just cheat. And the number of edges in G is P times some P times A times B. So what I'm going to do is to sample 2 random vertices in A without replacement, say. With replacement, sorry. So yeah, possibly the same 2 vertices, and look at its neighbors. So say this is some x, and my y is the neighbor set of x. So my claim is that sampling the 2 vertices in here and look at its neighbor is kind of powerful to argue that there is some nice set of vertices to start my embedding of H. So that's the basic plan. So let's say my H looks like this, the bipartitions say A prime and B prime, and say that here we have h vertices, and here we have the so max h vertices with max degree 2. So max degree 2. Sorry, this should be h vertices. Yeah. So this is a plan. And yeah, so my claim is that y is good. What's good is I'm going to say that a pair of vertices in y is bad if there's not enough space to avoid degeneracy, which means the size of the common neighbor of u and v is at most h. Less than h? Yeah, say less than h. I'm not terribly concerned with the equality. Yeah, so which means, so I'm gonna choose if my u1, u2, and some, so say, yes. Sorry, let me just say that this is h. So what I'm gonna do is to put these vertices in B on, to embed these vertices into the neighbor I picked, the set Y. And if I picked it in a correct way, then if all of these vertices are good, say H, are good, which means not bad. Sorry, I should have said that there exist these where every pair is good. It's not bad. Yeah. Then starting from embed these vertices in B prime to these many vertices, and I can choose the common neighbor to embed the others. And I can always choose a common neighbor while avoiding degeneracy because there are more than h vertices to choose. So I have plenty of choices which already exceeds the number of vertices in H. So I can always avoid degeneracy while embedding. So that's the plan. So if this is true, then I'm done. So let me just repeat. So embed B prime to these vertices and just choose my A prime by some greedy algorithm.
So your H, so the graph H is
the bipartite graph
right,
with max degree 2 on one side.
Yeah, so the small h is the number of vertices on the other side, right?
There are two h's in here, so I just didn't want to care too much, so I put a loose upper bound of the whole number of vertices. Yeah, yeah. Well, it can be precise if I put h1 and h2. Yeah, but I don't care because I'm just gonna give a very rough estimate. Yeah. Yeah, but to be very precise, it's correct. Yeah, so this is a plan. And let me just estimate the expected number of bad pairs. Pairs in Y.
Wait, still, I mean, you're finding U1 up to UH, right? You try to find H vertices, which are pairwise, not bad, right?
Yes. And that's plenty of vertices to embed B prime. Because B prime is again.
It's more
Yeah.
Okay.
Yeah. So what I need is just
Right,
this. Yeah.
okay,
Yeah.
correct.
Yeah. Yeah. So let me estimate the expected number of bad pairs, and that's the sum of UV in B, the probability, sum over all bad pairs, UV bad, then the probability that both U and V are in Y.
In the definition of bad pairs, if the UV is less than H or less than the size of A prime.
Yeah, I mean, to be precise, that should be like that, but I'm not terribly concerned with these little small terms, so as long as it's just larger than H, I'm just fine. Yeah. So the expected number of bad pairs is like this, and the philosophy behind this technique is that if the pair is bad, then there is a less probability that I sample these two guys in Y, because I sampled some vertices here. So if they have a small number of common neighbors, then the probability that they both belong to Y is small. So this is at most the probability that the bad pairs are sampled, which means the co-neighbor of these two guys are at most H, and because I sampled twice, so these red vertices must be in the common neighbor of these bad pairs, which means at most H over A squared. Yep. And another rough estimate here is I'm just going to consider all the pairs in B. So that gives an estimate of H square B square over A square. So that's an estimate. And so the second part of the argument is my Y is large enough, compared to the number of bad pairs. So this expected size of Y is let me average the size of common neighbor over all pairs in A. So that's the expected size of Y. And there's a simple convexity argument gives a lower bound for this term, which is as follows. So by this, what I'm counting is actually the number of K2 ones where two vertices are in A and the one vertex is the degree 2 vertex is in B. Right? So, and by hand waving argument, whatever, I can say that this is actually the degree squared. Yep. Because I'm just going to pick one vertex first and then pick the two leaves later. And that allows us to apply the simple convexity argument, which is and I should have B here and A squared. So this is by convexity. So I applied, if I divide these size of B on each side, then I get the average of degree squared. So expected degree squared is larger than be expectation squared. And because this is just nothing but the number of edges. So that's PAB, and that's divided by B, and P square A squared, and hence I have P square B. Yep. And what I'm gonna do is to compare this number with that. So in Y, there are just, yeah. So what I'm gonna do is, as long as this is larger than the number of bad pairs, I'm gonna just kill all the bad pairs by deleting one vertex from each bad pairs. And if that leaves us some sufficiently many number of vertices, then I'm just gonna pick each of them to embed B prime. So that's the strategy. So what I need to complete this argument is this P square B is asymptotically larger than H squared B squared divided by A squared. And this estimate gives so let me consider H as just constant, and then this is just a constant. Say, this is just a constant. And my B is roughly N, say. Then that gives us that P, as long as P square N is larger than some constant, larger than some large constant, then I'm happy. So that gives us some large constant times N to the minus half. So if this holds, then I can say that this is larger than that, and hence after deleting one vertex from each bad pair, I'm left with constantly many vertices to embed B prime, and I'm win. So this is the argument by Alon, Krivelevich, and Sudakov. And well, this is nice and relatively simple, but we still have to improve this bound. So another ingredient of our proof is the Ramsey theoretic concept of locally dense graphs. So here's our strategy. So to embed one subdivision of KT, we're basically going to do the same. So here's my G, a bipartite graph on A union B, and I want to, so the one subdivision of KT, which is HT. So I want to choose T vertex side in A and the other degree 2 vertices in B. And well, what I'm going to do is to make an auxiliary graph on A. Which means, actually, it starts from weighted graph. So for each pair, I'm going to just put the number of co-neighbors, the number of common neighbors. So if there are 2 common neighbors, I'm going to put weight 2, and so on. And if I find KT in A, then it's kind of successful, not yet complete, but it's kind of successful in a sense that if I choose T vertex, so if I have KT in here, if I embed KT here, then it's kind of successful. Because at least I succeeded in the make a non-degenerate-ish. I mean, it's non-degenerate on the side of T vertex side, but possibly degenerate on the other side. But if I'm successful, then this might give a copy of one subdivision of KT. And that's a strategy. So, and to do that, I mean, to find the copy of KT here, we borrow this concept of locally dense graphs from Ramsey theory. So what's locally dense graph is my graph is rho-d dense if for any rho portion of vertices, so let's say my graph G is rho-d dense if any rho portion of vertices for any U with rho portion of vertices that the edges induced in U has at least so the induced graph on U has density at least D. So here the half vector is because of the labeling issue. So yeah, so this is a definition of locally dense graph. And again, there's an easy argument that proves this auxiliary weighted graph is locally dense. So let me just sketch a proof of that if I have some time. So this lemma was firstly observed by in the work by myself and David and Jungbom Lee and Jong-an Kim on the work of Sidorenko conjecture. So the lemma says the auxiliary graph is locally dense. I'm going to specify the parameters later. So the reason is as follows. So if my G is here, and suppose I counted the number of K12s. Sorry, I'm going to start with U, some U in A. And that's A union B. And so this is modulo some technical conditions. G has minimum degree delta. And one kind of tip is that when you deal with this extremal graph theory question, it's fairly likely that you may just assume that your minimum degree and maximum degree is off by a constant from the average degree. There's a standard lemma by Erdős and Szymonowic, which allows us to assume so. So by the lemma of Erdős and Szymonowic, we may assume that there's a minimum degree not ridiculously small. And another one, so let me just look at the vertex set here. And because of the minimum degree condition, there exists at least delta times U, the size of U, edges from U to B. And what I'm going to do is to count the number of K21s like this. Sounds quite familiar? Yeah, so it's basically the same argument as given here. Yeah, so by convexity argument, I can give a lower bound for K21s that look like this. And by doing so, I can prove that within here, my weighted auxiliary graph is locally dense. So if I look at the weighted version of this lemma, then I should say that the sum of weights in U for the pairs of U. Yeah, so that's a statement. Then let me be a little bit more precise. So So here's a thing. So this is this much dense. Rather than giving a full proof, let me just explain what's next. because it's just simple convexity argument that you could just do. Yeah, so my graph is that much dense, and what I'm going to do is the standard Ramsey type argument to find the KT, which means I just pick one vertex and look at the neighbor. And if the neighbor is large, the neighbor set is large. What I mean by neighbor is the set of vertices that has non-zero weights on the pair of, that incident with this vertex. Yeah, if this is large enough, then by the local density condition, I can guarantee that there's an edge. So we found a triangle, and so on. So this iteration of this argument will give you KT. So starting from one vertex, look at the neighbor, and because of the local density condition, I have dense induced graph here, and look at one vertex and look at its neighbor. And again, if this is large enough, then I would have some edge here, which gives you K4, and so on. This is a standard Ramsey type argument to find a copy of KT. However, here's a very serious problem. So I dealt with weighted graph, and if my weights are too large, so note that I haven't really normalized anything, so my weight can be as large as n. So if the weights are too large, then I'm in a trouble because the size of neighbor can really shrink. Because if there are only few heavy edges with large weights, then even if I look at the neighbor, the neighbor set can be very small. And this makes serious trouble in applying the standard Ramsey type argument. And thus, we have to say that these heavy edges are not that many. And that's where another variant of this dependent random choice lemma comes in. So I think I don't really have much time, so let me just write down the lemma, which looks kind of fair. And just say a few words. Yeah, so here's a key lemma, which is for any bipartite graph H with max degree 2 on one side, and my G is bipartite on A union B. Let me just assume that A the same, but in the actual proof, the A and B are just off by a constant from each other. Yeah, then the number of homomorphisms, if you don't know what homomorphism is, then you may just assume that the number of copies in copies of full cycle, which is more or less the same. So then there exists C such that my M is C times log n. Then G contains a copy of H. H subgraph. So what does it say? So as I told you, the problematic case is when some weighted edge is very heavy, which means if this is heavy, if this is a heavy pair, and that exactly means there are a large number of common neighbors of that pair. And overall, by averaging, this boils down to the homomorphic number of full cycles in G, if you believe me. Yeah. And then if that's large, so what does large mean? Is if it exceeds the number of K12s, which means my homomorphic copies of 4 cycles can be just come from those of K12s if they're degenerate. However, if it sufficiently exceeds the number of K12s, which means there are true copies of 4 cycles, then G must have a copy of H as a subgraph. So if it exceeds this threshold, and then we have an H copy. And hence, if there are lots of heavy edges, then we win by this lemma. And very roughly, if there are just small number of heavy edges, then we can apply this Ramsey theoretic technique to find a KT. And well, I still have one step left to say that the degree 2 vertices are non-degenerate. But that's done by simply counting the number of degenerate copies. So for example, for 6 cycles, say, if I found a triangle on one side in the auxiliary graph, then it extends to an auxiliary, so in this triple in the auxiliary graph extends to a homomorphic copy of C6, which is non-degenerate on one side. But if it's degenerate, then what I'll get is there's one vertex here and 3 vertices like this. Yeah, so if this is degenerate, then I'll have these graphs. And I can actually count the number of these degenerate copies, and by comparing the number of these extendable triangles, I can say that there's no degenerate copy. So that's a sketch of proof. So let me just wrap up by adding some concluding remarks. So obviously, the one question of ours is, can you do the same with KRR-free graph H? Which means the external number is the order of 2 minus 1 over r minus some constant. So we believe that this should be true, but we didn't know how to prove it. So to deal with this case, one should have to deal with a hypergraph on one side rather than a graph, like R uniform hypergraph, which makes it more tricky. And there's a very recent proof by Janser, a student in Cambridge, who actually reproved our result with a fairly shorter proof and a better bound. But he still uses this Ramsey theoretic framework of locally dense graphs. So he's in the framework, but he has done a better job in deal with these heavy edges. And so our bound is the one subdivision of HKT with something like, so that's half, something like this. However, his proof gives much better bound. Yeah, that's actually linear when you take the reciprocal of the small constant, whereas ours is exponential. Yeah, and I think this is it, and times, yeah, right, this is it.